Hi, this is Dr. Kunka Bheemalingappa. I heartily welcome you. Present topic would be proving that NFA and epsilon NFA, they both accept the same language. We have seen for the given regular expression, at first we are going to construct this epsilon NFA. And we are known that design of this epsilon NFA for a given regular expression is very easy. And then we are going to convert this epsilon NFA to NFA and then NFA to DFA. We are known that the same language should be accepted by this epsilon NFA, NFA and DFA, whatever the language that is accepted by regular expression. And in one of the previous videos, I have explained how to convert epsilon NFA to NFA. It is better to go through that video once before you go through this video. I'm going to share that link in the description. You can just go through it. Yeah, coming to this, these are the contents. First, we are going to look at what is this NFA and then what is epsilon NFA, what is the basic difference between the two. And then we are going to prove that NFA and epsilon NFA, they both accept the same language. Coming to NFA, we have seen the definition of this NFA, also DFA and also epsilon NFA in one of the previous video. So the definition, the basic, but mainly in today's session, we are interested in proving that NFA and epsilon NFA, they both accept the same language. The basic difference between NFA and epsilon NFA is that in epsilon NFA, you will have transition on epsilon. Transition on epsilon. We are known what is this epsilon. Epsilon is an empty string whose length is of 0. Whose length is of 0. Right. Now, we look at what is this NFA. We recall what are the definitions of this NFA. If I let this NFA as say M1, we are known that this NFA is a phi tuple. NFA is a phi tuple. What is that phi tuple? Set of states, input alphabet, transition function, start state. So this is small q, this is capital Q. Capital Q denotes a set of states. And then set of accept or final states. These are the symbols that what we have in this NFA. So as I am using M1 as a shorthand notation for denoting this NFA, let me use this same subscript for denoting the rest of the symbols in this phi tuple. This is Q1, this is A1, right? So this is the NFA. And you are known the definition of this NFA. What is the transition function you are using? That is delta 1. And one more thing, here you have listed 5 elements. This is a phi tuple you are known. The order you don't need to follow, it is up to you. Right? But there must be 5 things, or say 5 elements. So coming to this definition of this NFA, we are known the definition of this, the transition function of this NFA is denoted with what? That is okay, delta 1. Therefore, the transition function of this NFA can be defined as follows. That is delta 1 star of say Q, say YA for Y belongs to sigma star, Y belongs to sigma star, and A belongs to sigma, A belongs to sigma. Very careful about the notations that what I'm using, whether it is a sigma, belongs to, or epsilon. All they look like okay similar, or don't get confused. Be aware of what symbol I'm using, right? So delta 1 star of QYA is equals to union of R belongs to, here the transition function is not delta, it is delta 1. So R belongs to delta 1 star of QY delta of RA, delta of RA. This is the transition function of this NFA. In a similar fashion, delta 1 star of being delta 1 is the notation that I am using here. Delta 1 star of Q epsilon. See, this is the symbol that what I am using for epsilon. Delta 1 star of Q epsilon is Q itself. Delta 1 star of Q epsilon is Q itself. And also you are known delta 1 star of QA for single input symbol. Delta 1 star of QA is equals to delta 1 QA, delta 1 of QA. With respect to one input symbol, there is no difference. That is what we came to know, right? So this is the definition of this NFA. This is the definition of this NFA. This is about NFA. Now, let us first look at what is the definition of this epsilon NFA. Epsilon NFA. Yeah. Epsilon NFA, I'm going to denote with, say, M2. M2. This is also a phi tuple. Q, sigma, transition function delta, start state, and a set of acceptor final states. So I am using the subscript 2, that is M2. So for elements in the tuple also I am going to use the subscript to avoid the confusion. Q2, sigma 2, delta 2, say this is small q, that is the start state. This is a set of acceptor final states. We know the basic difference between epsilon NFA and NFA. In epsilon NFA, we will have transitions on epsilon. But in NFA, we won't have transitions on epsilon. That is the basic difference between this NFA and epsilon NFA. Now, so what is the difference in this input alphabet? I can say in epsilon NFA, you will have transitions on epsilon. Therefore, I can say there is epsilon 1, that is input alphabet of this NFA. That is sigma 1 is equals to sigma 2 union epsilon. That epsilon will be extra here in epsilon NFA. That's what I can say. Otherwise, say epsilon 2 union, sigma 2 union epsilon is equals to sigma 1. That is input alphabet of NFA. Now, we are going to look at the definitions of this epsilon NFA. So, in the previous video, I have used this transition function name as delta. Here I am using delta. So, delta 2 star of Q epsilon is what? Epsilon closure of Q. So in case of NFA, transition function, that is delta 1 star of Q epsilon is Q itself. Here it is not just Q, it is epsilon closure of Q. So that is an important note we have to make. Next, coming to this delta 2 star of say Q, say YA or say XA. For Y belongs to same thing. Y belongs to sigma star and A belongs to Y belongs to sigma star and A belongs to sigma. This is epsilon NFA, so it can be stated as follows, is equals to what? Epsilon closure of, you're going to have this epsilon closure 2 times. Make a note. Epsilon closure of union of R belongs to. So this is the symbol that what I am using for belongs to. So be careful. R belongs to epsilon closure of Q, epsilon closure of Q. What is a transition function name you are using? That is delta 2. Therefore, it becomes delta 2 of R A. This is the transition function of this epsilon NFA. These two formulas are very important. We are going to make use of these formulas in proving our theorem. That is this. Delta 1 star of QIA is equals to union of R belongs to delta 1 star of QI, delta of RA, and also this. You are known delta 1, I am using for NFA. Here delta 2 I am using for epsilon NFA. That is delta 2 star of QIA is equals to this. Epsilon closure of union of R belongs to epsilon closure of Q, delta 2 of RA. So with this knowledge, now we are going to prove NFA and epsilon NFA, they both accept the same language. One more important thing, I think you remember while I was explaining about conversion of epsilon NFA to NFA, I have used this. Here you are known A2 is the set of final states of this epsilon NFA. And A1 is the set of final states of NFA. We have the conversion from epsilon NFA to NFA, right? So there you have seen A1 is the set of final states of this NFA. So from the final states of this epsilon NFA, you are going to get the final states of this NFA. So what the rule it says, A1 is equals to, that is you are known what is the final states of this epsilon NFA, that is A2 union, you are known what is the start state of this epsilon NFA, that is Q2, A2 union Q2, if this is the condition. What the condition it says? What the condition it says is this. Epsilon closure of Q2 intersection A2 is not equals to pi. Epsilon closure of start state of epsilon NFA. You are known start state of this epsilon NFA is, that is Q2. That is epsilon closure of Q2 intersection. This is intersection. This denotes that is intersection. Intersection A2. You are known, right? A2 is what? It is a set of final states of this epsilon NFA. If it is not equals to pi, be careful, it is not equals to pi, then your Q2, that is the start state of epsilon NFA, will also be the final state in NFA. That is the reason it has been given as A2 union Q2. Otherwise, just A2. That is, whatever you have the final states you have in epsilon NFA, they will become the final states of this NFA. But along with them, the start state of this epsilon NFA will also become the final state of this NFA. So whenever you can reach any one final state in epsilon NFA from the start state of this epsilon NFA only on epsilon transitions, then the start state of this epsilon NFA will also be the final state in NFA. That is what this. So with this knowledge now, moving on ahead, if they both accept the same language, what I supposed to prove? Delta 1 star of, you are known, I am using delta 1 for NFA, delta 2 for epsilon NFA. So if they both accept the same language in the sense, delta 1 star of Q, what happened? Yeah. Delta 1 star of Q, X must be equals to what? Delta 2 star of QX. QX. X belongs to what? Sigma star. So that is input alphabet. Input alphabet is going to be the same. If I let X is equals to epsilon, X is equals to epsilon, this formula may not be correct. This formula may not be correct because you are known delta 1 stands for NFA, delta 2 I am using for epsilon NFA. You are known delta 1 star of Q epsilon is just Q, whereas delta 2 star of Q epsilon is epsilon closure of Q. So there is a difference between just Q and epsilon closure of Q. Therefore, when X is equals to epsilon, this formula may not be correct. This formula may not be correct. So that is the reason I am going the proof for, that is proof by, that is structural induction on X. So I think you are clear, okay, till this stage. Till this stage. Better let me take the new slide. I think you are clear till this stage. Yeah. So that is a mathematical proof by mathematical, okay, induction, that is structural induction on hypothesis we say. So that way, right, we are going to prove. So for X belongs to sigma star and A belongs to sigma, I can make an assumption that if they both accept the same language, that is delta 1 is the transition function of NFA. So delta 1 star of, I make an assumption, delta 1 star of QA is equals to delta 2 star of QA if they both accept the same language. And with respect to only one input symbol, you are known there is no difference between star and without star. That is, we are known this, okay, delta 1 of QA is equals to delta 2 of QA. Because you are known delta 2 star of QA is equals to delta 2 of QA, and also delta 1 star of QA is equals to just delta 1 of QA with one input symbol. So this is an important formula. I can give some name for that, okay, later. Yeah. This is the assumption that what we have made. So induction on hypothesis in the sense we are going to make an assumption and then we are going to prove that. So this we can treat it as, okay, base step. This is the base step. This is the base step for induction on a hypothesis. Now we assume, so if this is true, then this must also be a true, right? Yeah, let me use it for, this is basis. Now I am going to moving on to, that is induction on a hypothesis. So what I am making an assumption here is delta 1 star of Q Y is equals to, we make an assumption this delta 1 star of Q, just like for one input symbol you have made an assumption, no, they both accept the same language in the sense equal to one another. So delta 1 star of QY is equals to delta 2 star of QY. Delta 2 star of QY. So with this assumption, now we wanted to show that this is, yeah, delta 1 star of QY YA is equals to delta 2 star of Q YA. This is what I supposed to prove. This is what I supposed to prove, right? So let us consider this left hand side part, what it says. That is delta 1 star of QYA. You are known delta 1 is the transition function of NFA. Delta 2 is the transition function of epsilon NFA, right? Now, I made one assumption, and then if this is true, then I have to prove that this is also true, right? This is what the assumption I have made. That is delta 1 star of QY is delta 2 star of QY. So I have to prove this delta 1 star of QYA is equal to delta 2 star of QYA. So delta 1 star of, that is what. So consider that left hand side part, that is delta 1 star of Q1 YA. Yeah, if you want you can write here. Consider, that is left hand side part. Left hand side part. What is that you have? That is delta 1 star of Q YA. X belongs to sigma star and also Y belongs to sigma star. You can use X or Y. Here I am using Y. It is up to you. So delta 1 star of Q YA. I have to prove. You are known this delta 1 is a what? Transition function of NFA. You are known the definition of this NFA. What the definition it says? Union of R belongs to. So what I am using here, delta 1, right? Not delta. So R belongs to delta 1 star of Q Y, right? Delta 1 of, be careful, this is delta 1 of R A. So this is from the definition of this NFA. You are known NFA is delta 1 is the transition function of NFA, right? So how I have written this in the sense, this is from definition, right? If you want, you can write about that. From the definition, right? I have got this, right? So next, this in turn can be rewritten as what? Yeah, in the basis, yeah, in the induction, I made one assumption. What is that assumption I have made? That is delta 1 star of QY is equal to delta 2 star of QY, right? So from I can rewrite this. That is, let me use a different color. Yeah, union of R belongs to. Just now, right? You have seen delta 1 star of QY is equal to what? Delta 2 star of QY. Therefore, I am going to replace this delta 1 star of QY with what? Delta 2 star of QY. Delta 2 star of QY. That is this. I have replaced this part with this part. That is delta 2 star of QY. And then from the base, you are known. From the base, what you are known? Delta 1 of QA is equal to delta 2 of QA. Delta 1 of QA is equal to delta 2 of QA. Right? So from this one, I can rewrite this. What you have here, delta 1 of RA. There you have Q, here you have R. That is the only difference. So whenever you are known, that is delta 1 of QA is equal to delta 2 of QA, in the sense, delta 1 of RA is going to be equal to what? Delta 1 of RA is going to be equal to what? That is, let me use a different color, this one. So what can I write? Delta 1 of RA can be rewritten as what? Same color as, yeah. Delta 2 of RA. I think you are clear. Delta 2 of RA. So what you have got? Union of R belongs to delta 2 star of QY, delta 2 of RA. This is what you have got. Right. Next, moving on. This delta 2 is a what? Transition function of this epsilon NFA, right? Delta 1 I am using for NFA. Delta 2 I am using for what? Epsilon NFA. And you are known the definition of epsilon NFA. In the definition of epsilon NFA I have written. You can just recall. Yeah, this is what. What I have written here. Delta 2 star of QYA is equals to this, right? So here if I take this Y as epsilon, yeah, in this equation, if I take Q is equals to R and R is equals to P, then I can rewrite this equation. I think you are clear. So delta 2 star of QYA is this. This is what you have got. So in this formula, wherever this R is there, I'm going to take that is Q, and wherever this R is there, I'm going to use this P, because already you are using this R here. Therefore, I cannot use this R, right? So if you are going to rewrite this, right, as per that. So if you want to give some name for that equation, right, you can give, right, so that there won't be a confusion, right? If you want to call this equation as, say, C, you can call C. So from C, in C, if you are going to take, that is Q is equals to R, right? Let me write here. If you are going to take, say, Q is equals to R and R is equals to P, if you rewrite that formula, then what it becomes, this part is as it is, this part union of R belongs to delta 2 star is as it is. Let me write that part at first. R belongs to delta 2 star of QY, just is as it is. Just in place of this delta 2 RA, there I have written a formula that is delta 2 star of QYA. Here Y is epsilon, right? So then what it becomes? It becomes this. You can just make a comparison. Epsilon closure of, let me use a different color. Yeah. Epsilon closure of union of. So I am using P in place of R in the formula and using R in place of Q. So as per that, you are going to get, that is a P belongs to epsilon closure of R, delta 2 of RA. Here for delta 2 you are writing. There you have, that is delta. So if I let that is no change, right, with respect to delta 2 here. So delta 2 of PA. Here P belongs to, I am saying, therefore I have to use this delta 2 of PA. This is what the formula that what you are going to get, from that one. I think you are clear till this point. This is how, right, you are going to get. And in converting that epsilon NFA to NFA, have seen the epsilon closure operation has the property that the union of epsilon closures is epsilon closure of the union. Here you have union and then epsilon closure. So from this property, that is the property of epsilon closure, what it says, the union of epsilon closures is epsilon closure of the union. Suppose, for example, you have states as, say, 1 and 2. Epsilon closure of 1 you can find, epsilon closure of 2 you can find separately. And then if you take the union of this epsilon closure of 1 and epsilon closure of 2, you are going to get that, you are going to get something which is going to be same as, that is directly finding epsilon closure of 1 union epsilon closure of 2. I think you got my point. It is going to be the same. That is the reason this union and epsilon closure they can be interchanged, being they are giving the same result. Union of epsilon closure is epsilon closure of the union. Therefore, just I'm going to rewrite this formula, that's all. I'm just going to interchange epsilon closure and union. Just change the order. At first you have union and then you have epsilon closure. I'm just going to interchange this because union of epsilon closure is epsilon closure of union. Therefore, I can rewrite this as what? Epsilon closure of, just I'm taking this epsilon closure that is inside, I'm taking it outside. Epsilon closure, let me separate this otherwise, because this is, epsilon closure of, just I'm changing the order. Union of, rest of the things are same. R belongs to delta 2 star of Q Y, delta 2 star of Q Y, and that part as it is, right, I'm taking, that is what, that part, that is union of P belongs to epsilon closure of R, epsilon closure of R, delta 2 of PA. This part as it is, right, I'm taking delta 2 of PA, delta 2 of PA. Only I interchange the order or say position of the epsilon closure and union. I think you understood. This is for this part. So epsilon closure of this, here I have opened this bracket. Let me close that bracket there. So that is what this. And this epsilon closure of R is a subset of this delta 2 star of QY. Therefore, you are known here, you have two unions. These two unions are unnecessary. You can just have only one union. You can just have only one union. Therefore, this can be rewritten as, let me, make it separate block. Yeah. Two unions are unnecessary, I am saying. Therefore, this can be rewritten as what? Epsilon closure of, I have given the reason. Since this delta 2 star of, this epsilon closure of R is a subset of this delta 2 star of QY. Therefore, two unions are unnecessary. So, I am writing epsilon closure of, I am going to put only one union. That is, this is bracket, union of R belongs to delta 2 star of, be careful, delta 2 star of QY, delta 2 of, here whatever you are writing, that same thing you have to write. R belongs to, you are saying, therefore it becomes delta 2 of R A. Delta 2 of R A. This is what it says. Two unions are unnecessary. I just eliminated, and also this is a subset of that. So for that reason, I am eliminating one union. So this can be rewritten as this. This is a formula of what? Epsilon NFA. What the delta star of QYA, what it says? Epsilon closure of union of R belongs to delta 2 star of QY, delta 2 of RA. So this can be, this is from the definition of epsilon NFA directly in the list of formula I have written. Therefore, this can be rewritten as what? Delta 2 star of QYA. So I started my derivation with what? Delta 1 star of QYA, but from that I got delta 2 star of QYA. Hence the theorem, I can say. Hence the theorem. Thank you for watching the video. Wish you a good day.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.